this problem is something like this. 65, you know, we've got, you know, 75, and then 95, 64, just like we did the last one, you know. 17, you know, 47, right? Does this configuration make sense to you, how I'm writing this down? Or sorry, scrawling this down because it's barely legible. Okay, so now one thing that we did learn is that, or that was pointed out, or maybe we haven't pointed out yet, is that the problem longest path is NP complete. Which means which means currently all the best algorithms we have are going to be c to the n power, right? However, it does say that like there's a brute force that doing this, and that's certainly true if you're trying to do this brute force solution. But it says that there's an efficient and clever algorithm you can use, and this has to do with the fact that just because a problem appears to be just appears to have the same goal, which is find the longest path, it doesn't mean that particular instance of the problem is NP complete. Does that make sense? An instance of a certain instances of a problem can be easier than another. For instance, the graph we're drawing here for this problem is a directed acyclic graph, right? And yeah, it radiates out, but it's a directed acyclic graph, which means that we can really use, dynamic programming and basically we can solve this in basically linear time, where n is the number of items we have to solve by just looking at all the previous because once we solve each layer, we can use that information from each layer to solve the next layer. So for instance, 75 plus 95, okay, we know that the best, this best is 75, right? The cost to get to this node is 70 plus 5 plus 95, which is 170, right? And over here, that cost is 139. This is how you know that I've really gotten that things have gone really bad. The arithmetic is easy. The better you're feeling, more comfortable you're feeling with higher mathematics, the harder the basic arithmetic is. Hi. Okay. Great. We can actually start now. All right. And then finally, I'm going over the homework that I've signed. I've signed the last homeworks for the semester, by the way, both of them. As far as presentations, if you haven't done a presentation, we'll do them next Tuesday, both of them. Okay. So, because then so here we're going over the maximum path problem, and I pointed out that yes, this is a longest path problem, which is one of those NP complete problems. But not all instances of NP complete problem, not all formulations of NP complete problems are the same, right? This is a clever solution because it's a directed acyclic graph, and the idea here is finding the longest sum. We can go through and basically solve each layer, right? Once we've calculated out that this best way to get the best route to get to here is 170, we don't have to recalculate it because adding in additional nodes or points of information isn't going to make us backtrack. Whereas longest path, when we've got a generalized problem, if we had a edge that looked like this, we would definitely need to backtrack or something to figure that kind of stuff out. Make sense? But here it's directed and acyclic. Okay? So we can turn this into a graph. Now, or if you don't want to turn it into a graph because you're born like me, you can instead use an array and basically say, a jagged array. So index 1 over here. So here's our index 0, 0. And then index 2. Index 2 has our index 1 has our second list in it, which is 75 plus 95, which is these values over here, okay? These values right over here, right? 75 plus 95 becomes 170 and 139, right? And now we have our third list. Notice that the shape of the triangle becomes a right triangle as opposed to this isosceles triangle? Oh, no? So anyway, so over here, 17, we would be like, we can do 187, and then we'd have to check the comparison of which of these is bigger. Is it big? So we've got, so what I'm saying is that we've got this 47 value over here, okay? You've got this 47 value over here. So you got to ask, is it better to add 170 plus 1, is it better to ask 170 plus 47 or 139 plus 147? Obviously, it's better to add the biggest number, so 120. Two. Yeah, again, my brain has been fuzzy ever since I got COVID. It goes a bit slower than it needs to. The idea here is that we can formulate this problem and we can go through layer by layer. We don't have to redo our work again. This does not end up being an exponential time. Problems can often be easy. Just because a problem is NP complete or the general formulation of a problem is NP complete, that doesn't mean doom and gloom. So we're going to recap a bit for NP completeness. So I've shown you two ways. The first is to convert it into a graph like we've seen for previous problems, right? And then just kind of go through and figure out what the biggest value is. The second is just turn it into an array, or a table like we do for all dynamic programming problems. For Thursday, we'll have a quiz on dynamic programming. For that one thing that I know I'm going to ask you to do is to basically go through and kind of solve the knapsack problem by hand. Like and I think, now do you want to do we're going to do the 0-1 knapsack problem because that requires you to actually make a table. So 0-1 means you can either, here's an inventory of item, you can either take an item or not take an item, right? So you want to go through and solve, okay, here's the optimal solution for weight 1, here's the optimal solution for weight 2, optimal solution for weight 3. That may be the only, given the time constraints, this may be the only problem that I give, a knapsack problem, basically solving the knapsack problem by hand, okay? So expect to be able to do that. Go review your textbooks on the knapsack problem, but our last quiz will be on the knapsack problem. Okay, for the final exam, we can discuss other things about what to do that. All right, anyway, let's go ahead and talk about problems. Okay, review our problems. So we've got ourselves a kind of graph that I'm stealing from MIT's 6006 course, which is fantastic on this material. Now, we have these different kind of classes of stuff. And what we care about, and this is a graph of decision problems. And the reason we care about decision problems is that they have and you're wondering, why do we care about these decision problems? Why are we phrasing everything in yes-no questions? And the answer is because we've got actually a history longer than computer science studying this stuff, in terms of whether something is decidable or not. In fact, what we're going to do is we are going to basically, I'm going to make my first mark out here, kind of, and call it R. R is the set of problems decidable in finite time. The problems we can Notice that basically there's stuff that is beyond R, okay? So kind of think of R as like this subset over here that kind of encompasses a whole lot of problems, okay? R is all the problems that are decidable in finite time. Why is it called R? It comes from recursive languages. Let's go back into history in a second. There is a bunch of famous mathematicians. Okay, so this is a bit of a history lesson. And there's this very specific problem called the, I think it's Entscheidungsproblem, or it's German for decision problem. Hey, that sounds familiar. Decision problem, posed by David Hilbert and Wilhelm Ackermann in 1928. The problem asks for an algorithm that considers as an input a statement and answers yes or no according to whether the statement is universally valid. An example of this is related to one of Hilbert's other problems, his 10th problem. He gave a list of mathematical problems that were posed. And it says, hey, given this Diophantine equation, which is not a term I've heard until like today. I've seen these kind of equations. You've seen them all their life. The idea here is, solve the equation with solve an equation with at least two variables in it. That's what this word means, Diophantine. An example of this might be solving ax plus by equals c, where a and b are given. Okay? An example that your textbook gives of this problem, like a literal, here's an example of this problem, like an instance. X, here's a polynomial equation, x cubed yz plus 2 y to the fourth, z squared minus 7 x y to the fifth, z equals 6. Solve for x, y. Find x, y, and z such that the equation is satisfied. So an integer version of satisfiability. So there's no algorithm that decides this. There's no algorithm that solves this. Oh, also x, y, and z, I should just mention, are in are in the set of integers. Okay, they're in integers. Make sense? X, y, and z are integers. Find integers x, y, z that satisfy this equation. There is no algorithm that exists that solves this. And by which I mean algorithm that, again, algorithms, well-ordered, well-ordered, unambiguous operations that solve something in a finite amount of time. No guarantee are the set of all problems that can be decided in a finite amount of time. Right? If there's a solution, I suppose we could write an algorithm that finds one, but it might be very big and we might take forever. Well, also, we don't know because we'd have to check every single integer trio, and there's infinitely many of those. Okay? There's no polynomial, no exponential, no double exponential. These are unsolvable. All right? The first of these unsolvable problems is actually discovered by none other than this dude you've heard so much about. Turing. That's why he's famous. It's pretty much why he's famous. When he solved this unsolvable problem, when he found this and defined this first unsolved problem, there weren't any computers, and in fact, you can argue that computers and all the things he's famous for came about because of this idea. So and his problem is the halting problem. All right. So given a input, so let's go ahead and assume. Let's take our favorite programming language. For me, it's going to be Python. And the idea here is we want to write a program called terminates. Okay, which given this is a program written in Python that takes in a Python program, okay? Takes in a Python program and and an input x, and returns true if the program terminates after running on x, or false if it does not terminate if it runs on x, right? So this tells me whether or not the program has an infinite loop on x. Make sense? Okay? So tells us whether or not it's going to stop. But how would we write this program? Okay? And it's worth thinking about. Trying to think of an infinite loop detector. And we're going to prove by contradiction that you can't. Right? Here's a proof that such an algorithm can't be written, at least by the way we define our programming languages under the models we're using. Okay? Which is, let's assume that this exists, that this is a magic black box that exists, and it will go ahead and answer my question. Then I can write a program called, I'll write a program called Paradox. This is what your textbook states, and it's very good. Where it takes in Z, a program Z, and a file. If and I'm going to just use bad notation here because I can. I'm going to use a harmful notation, in fact, because I can. Because it just makes it. So if terminates on Z and file. So if this program terminates, go back to line 1. Gochu is considered harmful, don't use it, but you get the idea. While the program terminates, continue a rerun, If the program terminates, run it again. This program now runs an infinite loop. So Paradox says it terminates if and only if it does not terminate when it's given itself as a source code. Okay? So now what happens if we do paradox of paradox? Does it stop or does it never stop? I mean, I named it paradox, so obviously it's a paradox. It's not gonna. It's a logical paradox. It cannot work. Right? Paradox terminates if and only if Z does not terminate. So paradox, we're feeding itself to itself, and the idea here is that you can't tell whether or not it's going to stop itself, or is it? It's contradict. We contradicted. We assumed we got to this contradictory result by assuming this program can exist. So by showing that if it existed, we get into a nonsensical state. It can't exist, at least in the current model of computation we have. This is outside of R. That's what this is what R is, and that's what lies outside of R. Okay. This is called the halting problem, which is, again, one of the most famous problems that you've probably heard of but not heard defined, right? You've probably heard it, of the halting problem, in passing at some point. And it points out that it is usually via, a key part of this is the formal definition of a computer and a Turing machine. Now we're getting into a bit of what automata is when we talk about a, Turing machine. One second to grab my appropriate printouts. thought this was the appropriate printouts, but one sec. Sorry. So there are, again, is the issue. We've got these problems. Oh, right, there we go. So a Turing machine is built it like a theoretical human computer. Currently, there's always a philosophical debate as to whether or not a human is a Turing machine. What the heck is a Turing machine? Or is a human something beyond a Turing machine? We talked a bit, we briefly mentioned finite state machines. Finite state machines are these kind of, things that, anything that can be operated in terms of states and flowcharts, right? Like over here with a turnstile to go through. I mean, we use, in Japan, at any rail station with an IC card, you use an electronic turnstile where it goes from locked to unlocked. Right? You tap your card, it goes into the unlocked state, you pass through, it's now locked again so the person can't go, so the second person can't go through. Right? You can push on it all you want and try to go through it while it's in the locked state, but it's going to stay in the locked state. Right? Ignore the fact that about jumping over the turnstile gate. That's not what we're caring about. We're not caring about people going over. That's not defined by this. What's defined by this is the whole operation of states. This is actually defined mathematically. We actually do define this mathematically using a lot of scary Greek symbols that aren't actually all that scary once you sit down and explain them. Sigma, S, S naught, delta, and F. Okay? The idea here is that you've got some input alphabet. This is your language that you use. In other words, these are things that you can use in your states. For this one, it is, again, your alphabet here is coin, push, right? That's your alphabet. Or zeros and ones, right? Typically it's zeros and ones when we're talking about it. S is your states. It's got to be not empty, otherwise it's useless, right? What's the use of a flow chart without anything to flow to and from? S naught, this third argument, is your start position. Delta says it's straight transition function. Simply put, it's saying, hey, given a state and it's just saying, hey, here's a function. It takes two arguments, a state and a symbol in the alphabet that gives you another state. Okay? And then F is your final state, something where we end this. Okay? This is pretty good, and in fact, regular languages are equivalent to these things, right? Anything that's a regular expression is essentially equivalent to these things, although regular expressions sometimes get extended into something that's what we see is called a push-down automata. Push-down automata basically is the same thing as an automata, but it has a little bit of memory. We add a little bit extra. And this is, again, I'm giving you basically the high-level overview of automata theory, the entire class into its own right, with one textbook used by everyone, Sipser. Sipser's textbook is used by everybody, Theory of Computation. Okay, but what's the important thing we have? We have now added a stack and its own alphabet and its own operations on a stack. Basically, it's saying, hey, a finite push, if we want to do something a bit more powerful, like recognizing in any programming language where we recognize, appropriate amount of parentheses matching, arbitrary length parentheses matching. That's kind of basically, have I opened and closed my parentheses correctly? Okay, that's too strong of a problem for your for your finite state machines. If you use a stack, though, basically every time you see a open parenthesis, you push it onto the stack. Every time you see a closed parenthesis, you pop the stack. This lets you count any number of parentheses arbitrarily. So adding a bit of memory is good. You add a second stack, and you get yourself a Turing machine, although he doesn't refer to it as a second stack. Instead, a Turing machine is essentially the same thing that we had, but now we have an infinitely long strip of tape that's made up of cells. Now, most of your computers aren't actually implemented as Turing machines. They're in random access machine. They use RAM. doesn't use an actual physical tape, but mathematically it works the same. And it has its own operations for things, but basically it's these language with now that we have this tape that we can mark off as memory. That's what a Turing machine is, and it's its own model. There are other models of computation, but they're equivalent. Turing's doctoral advisor, Alonzo Church, who coined the term Turing machine. By the way, interestingly enough, he's up the chain in my PhD advisor kind of ancestry. So the advisor of my advisor of my advisor of my advisor of my advisor, which means absolutely nothing because I wish, because God knows that these famous people had tons of things. But he had his own thing called lambda calculus, which is computationally equivalent to this, and the Church-Turing thesis, which basically says any algorithmic procedure that can be carried out by humans or a group of humans can also be carried out by these Turing machines. Basically, if you can do these pencil and paper methods, then we can do it. It's basically saying that we equate an idea of an algorithm means we can run it on a Turing machine. So that's what our R is, essentially. Although, again, there's a lot of stuff there. It's very complex stuff. It is a valid model. What would make it invalid? Probably quantum computation and stuff. Probably breaks that open and stuff. So we are talking about this. But most of the time, we're not actually just talking about things that are decidable. We know that this is a very big class of problems. Okay? Instead, most of the time, we're dealing with stuff in P. Let's see. Let's go ahead and actually mark this. Let's go ahead and mark in the rest of the markers over here. Most of the hard problems we look at are they're exponential, right? Exponential time. What does that mean? Basically, it means that anything over here can be solved in exponential time. Remember, we can overcomplicate any easy problem. You certainly have while programming at some point when you're a novice. You can overcomplicate anything and make it exponential, right? A good example of this is like the 8 queens problem. Play 8 queens on the chessboard. We can do an easy problem with recursive backtracking, which prunes out a bunch of invalid answers. Or we could check all 64 choose 8 possibilities, brute force, and that would be bad. Okay? And then we've learned about 2 things, NP and P. P meaning polynomial. NP does not mean non-polynomial. It means non-deterministic polynomial. Okay? It means that basically if we had a non-deterministic Turing machine, we'd be able to solve it in polynomial time. If we had a lucky Turing machine, one that always chose the right answer all the time, the right branch of the path to take all the time, then it would solve it in polynomial time. Another way of thinking of it, NP basically means that if it's an NP, we can solve it we can verify its answer in polynomial time. Okay? So, when you're programming, when we're talking about problems, you'll hear about 2 terms that refer to this dot right over here that I'm drawing. NP. Let's go ahead and I will actually use the colors they use in the MIT because why not? NP complete. And squares here. NP hard. Okay. So here I'm describing two sets. We have NP and we have NP hard. Okay? Now let's go ahead and talk about reductions again. When we say that a problem can be reduced to another problem, which is, say, if we can reduce problem A to B into problem B, sometimes written as A, which means that it reduces in polynomial time to another problem. In other words, if we can transform problem A into problem B, then that means that problem B has to be at least as hard, right? At least as hard. So, if you can take every problem, so what does it mean to be NP hard? NP hard means if we can take any problem in here, okay? Any problem in NP, okay? So anything at that point of NP and below, anything that can be solved in non-deterministic polynomial time. If you can transform it into, if you can take any problem and transform it into problem, let's call it problem B. So if you can take anything in the highlighted portion and transform it into problem B, that means that problem B is NP hard. So anything that's, if every problem NP can be transformed into B, if every problem can be reduced to B, then it's NP hard, meaning it's got to be at least as hard as the hardest thing in NP. Make sense? Okay. So where does NP complete come from? NP complete basically means has two clauses. So A is, so problem A is NP complete. And let me see. I'm just checking if that was an if and only if. I always forget. Well, I know it's definitely an if, so I'm going to write an if. If 1, A is in NP. So if we know that this problem is not deterministic polynomial, that's condition 1. Condition 2. Okay. See, all problems in NP reduce to, or in other words, can transform into, all problems in NP reduce to or can transform into A. In other words, A is NP hard. So NP hard is just clause 2 of this, meaning that all problems in it that are non-deterministic polynomial reduce into this problem. However, if we know that A is in NP, that means it only exists in one place, which is that intersection between NP and NP hard. Make sense? So NP complete means it's the hardest problems in NP. Okay? And because we already know that every problem in NP by definition transforms into that. So every problem in NP complete can transform into that. When NP complete was first, kind of not projected but presented, we had some, and in our slides we talk about how we have this very first NP complete formulation, which is where we have this very first formulation, and that is circuit sat, basically making a, we can define, basically the idea here is that we can define any problem in terms of a combination of and, or, and not gates. Think about that for a second. Every problem can be defined in terms of and, or not gates that can run on a computer, right? So, or at least not necessarily this, but not necessarily that every problem can be defined that, because you still have your exponential time problems, but you can think about it. My computer is made up of and, or, and not gates. So there's got to be a way to define problems in that term. So hence, that's kind of where we use this as their starting point. Satisfiability is a very good starting point for these problems. Okay? And the last thing I want to kind of mention as an aside before we move on to more NP-complete problems is this little kind of question. If this is NP-complete, does that mean that there's also a exponential complete and a p-complete? And yes, those terms just kind of fall naturally from the fact that there's got to be an exponential hard, exp hard. It's as hard as it's at least as hard the problems in exponential time. Similarly, there is that's a bit silly though, because we're already dealing with ridiculously hard problems like chess at that point. So what in the world is p-complete? Because p-complete, those are polynomial time problems. They're as hard as the hardest problems in polynomial. Basically, that means that, what would it mean to be p-complete? It would mean that every problem, a problem would be p-complete if that problem is in P and all the problems in P reduce to that problem. Make sense?
But it's not like no very necessary.
No, but it's a useful exercise for these kind of proofs. But what in the world are, but let's go ahead and just check those p-complete problems, because they're useful because they have analogs. Okay? They have analogs to these problems. Right? What are some p-complete problems? Given a circuit, the inputs to a circuit and one gate, calculate the output. Horn satisfiability. So notice that basically, so remember, we keep talking about satisfiability, which is, here's a Boolean clause. Is there a configuration of true false that that work for this? Horn satisfiability says, hey, it's the same thing. Is there something that satisfies this problem? Okay, but right. So satisfiability, right? Give me things. Okay, right. Here's the satisfiability problem, right? Given these clauses, right? Give me a configuration of x, y, and y's, and whatever those are that give me truth. Or is there a configuration of these Boolean variables that give me a truth? Horn simply says the same thing. Give me settings for these true false, but they're in the horn clause format, which means they're restricted into what they can be. Namely that you've got basically a statement that's true. Then you've got something that says, hey, in any clause, only one variable can be true. So by limiting kind of the format, suddenly the problem's in P. And not only that, we know we can prove it's the hardest problem in P. Another one I really enjoy that I found out was in P by looking through this is the game of life. How many of you are familiar with the game of life? Yeah? Game of life is, it's not the game of life that is the, that's like the roll, spin. It's Conway's game of life, not the Milton Bradley game of life, not the one where you spin and try to get to the end with like the most money or family members or whatnot. Game of life is a cellular automata zero-player game, meaning you provide the initial configuration and it uses the rules to generate things. Basically, you've got a cell. Each cell has 8 neighbors, right? Because it's a grid, right? You know, if you've got a grid, you've got squares, and every square has 8 things surrounding it. It has 2 states, living or dead. If you have less than 2 neighbors, you die of loneliness. If you have more than 3 living neighbors, you die of overcrowding. Okay, and then if you have 2 or 3 neighbors, then nothing happens to you. And any dead cell with exactly 3 live neighbors becomes a live cell through reproduction. And what it does is that using these rules, it can just simply create these kind of patterns. Now, this entire kind of thing is actually Turing complete. It simulates a Turing machine. You can simulate a Turing machine on this with a lot of effort and no life, I guess. But the idea here is that, but again, you know, given one of the interesting things about this is decidable, is that it is very chaotic. The game, it's undecidable, given, just like, we're running into the halting problem again. Given an initial pattern and a later pattern, no algorithm exists can tell whether or not that later pattern will actually appear, right? Halting problem determines whether a program will finish running or run forever. It's just the halting problem rephrased. But interestingly enough, you've got easier versions of this problem. Given an initial configuration and a cell you want to look at, and a time you want to look at, is that cell alive or not? So it's actually pretty interesting. Oh, type inference, giving untyped terms, determine whether the term has a partial type. Okay, so we have a bunch of these. So we have some problems here that are interesting. So again, what we care about are those NP-complete problems. Those are the big ones because, again, they have a lot of historical baggage around them. So what are the big ones? The big one, to end them all, as we've mentioned, the big one, right, of all is, so there were 7 initial problems. The first one and foremost is SAT, right, which is given a clause, right? Given some kind of clause like this, X, Y, Z, some kind of clauses X or Y or Z, or A or B, and not A or B, and B and not C and not D, and so on and so forth, right? Just basically these are of varying length. This is, is there, can I set, for each of these variables, can I find a true-false configuration that will make this evaluate to true? Make sense? Okay? Now, now we can turn any SAT problem into 3-SAT. Okay? And 3-SAT says basically that every clause is made up of 3 variables. So like here we would have, we could have A, B, I'm going to do a trivial one, A, B, C, and B and C and D, right? And D and not E and F, right? It's not too bad. Right? The idea here is that, but everything is a triplet. Everything is made up of threes. So how can you go from clauses that have an unlimited number of clauses to clauses that have 3 clauses? It's not too bad, actually. This is actually a fairly straightforward way to show it. So we just need to look at each clause, kind of. So first off, obviously, if I'm in a clause like this, X or Y or Z, if I look at each clause and I decide to do something with it. Let me give myself some more space. So first off, right? If the clause looks like this, X or Y or Z, guess what? I don't have to do anything. It's already a triple, right? So then there's 3 other possibilities. It has 1 symbol. It has 2 symbols. And then it has A, B, C, D, so on and so on and so forth. Okay, symbols. So so for this, I need to turn this into a triple. That's actually fairly easy. Right? I just turned that if it's a unary symbol, I just turn it into, now it's a valid 3-sat clause. Similarly for this, I could turn this into my choice of either X or Y or X or X or Y, So very easy to turn these into anything with less than 3, to handle anything that's less than 3 symbols. For something more than 3 symbols, we need to do something like this. We need to do something, and you'll see the pattern very quickly. A and B, A or B or X1. You turn this into A or B or X1, and X, not X1, and C. So I've taken the and X2 and not X2 and D and X3 and not X3. Okay, so you see the pattern here? Where basically what I do is I take the first 2 symbols and then I add in a new symbol called X1. I basically add in a new symbol for each additional thing beyond what I had. And this ends up being logically equivalent to the initial statement. Where basically I take the symbol and then I knot it in the set to connect it to this clause, and then I have the X2 and knot it over here to connect them. And it ends up... How do you choose the variable?
The variable.
They're either true or false. They're new variables you add into the equation.
Well, it doesn't matter if they're true or false.
I mean, it matters whether or not they're true or false, but I mean, like, if you set X1 to true, and this will be false, right? And you can work it out, but it will be logically equivalent to this original statement, is the idea, okay? But the point being is that we can transform any satisfiability problem into 3-sat. Okay? And just and this is generally how you show a problem's NP complete, by transforming some NP complete problem into it. So what's the other problem? 3DM, or 3-dimensional matching, which is a generalization of the marriage problem. Okay, so let's go ahead and go back to the original marriage problem, which we didn't cover, which is basically as follows. Whoopsie. Okay, Suppose we've got some set of men over here and set of women over here. And for the sake of argument, even though it's much more complicated than that, we're going to assume that men like women and women like men, but men don't like each other and women don't like each other. Yes, it's more complicated than that, but for the sake of argument, we're going to assume we're in a very heteronormative society here. Okay? So the idea here is that we have Adam, Bob, Carl over here, okay, and we have Alice, Betsy, and Kathy over here. And the idea, and we'll put dots for more names, right? ABC. I'm just using ABC names. And the idea here is that these are nodes in a graph. These are bipartite graphs, meaning that we can divide it into two categories. Okay, and the idea here is that we'll draw a line between them if they're compatible. Adam's compatible with everybody. Adam likes everybody, and everybody likes Adam. We're assuming that these are undirected graphs. Okay, Bob only really gets along with Betsy and Carl, and basically the idea here is, can you choose a matching so that we can match everybody up so that everybody's happy, right? Bob is only compatible with Betsy, so we'll do that. Then Carl and Adam are very easy. We can just, ABC. If we delete this line over here, right, then suddenly our problem changes. And so we have to do this for a matching. And then if we delete this line over here, there's no possible matching, right? Make sense? So this is the kind of the marriage problem in general. The bipartite matching is what it's called. Bipartite matching, okay? Now, why do I bring this up? Because this is not too bad of a problem. This really isn't too bad of a problem over here in terms of figuring out whether or not a matching exists. But three-dimensional matching says let's abstract this to men, women, and pets. And in fact, we can't actually put it on a graph too easily. What we're going to here, and I'll show you what I mean. Let's go ahead and open up our algorithms textbook for a second, where it talks about this problem. Okay? And we'll go and get to a picture of 3D matching, which is, remember, and what we're trying to do here is choose edges. Okay. Sorry, over here. It's all the way. Here it is. So bipartite match. So matching, three-dimensional matching. Given a bipartite graph with n nodes on each side, boys and girls, and a set of edges, now here's the problem. In a new setting, there are n boys, n girls, but also n pets. And the compatibilities are specified by a set of triples, each containing a boy, a girl, and a pet. Intuitively, a boy, girl, and pet means that these three get along well. We want to find n disjoint triples and create n harmonious households. Can you spot a solution in 8-4? And it's a bit weird because here's our graph now. And we've got our boys over here, Al, Bob, and Chet, and then we've got our girls, Alice, Beatrice, and Carol, and Armadillo, Bobcat, and Canary as our pets. But notice that none of them actually touch each other, or as such. Instead, they connect to these triangles, where each triple where a boy, girl, and pet would be happy together is shown as a triangle. This is no longer a graph, or this is no longer a normal simple graph. This is what's called a hypergraph, where each of those triangles is actually a single edge. In a hypergraph, each edge can connect to more than one pair of nodes. Right? An edge normally just connects from source to destination. Here in a hypergraph, right, it becomes a bit weirder. But we don't need to know that to solve the problem. But here's what it kind of looks, what a hypergraph kind of looks like. We're kind of, notice here our dots are our vertices, and our edges are now, instead of being a line, they're a blob. We're still using the term edge because we want to use the same terminology. But it's more like smeared over here. You can see that edge 3, V5, V6, and V3, and I mean, but it still generalizes it. The idea here is that there's some kind of relationship that binds these three vertices together. Make sense? Relationships are, it's not a binary relationship anymore. It's some kind of other more abstract relationship. So here, this triangle says that Al, Alice, and Armadillo is a happy triplet. Okay? Right? And also, and this one over here says that Alice, Bob, and the armadillo is also a happy triplet. Make sense? And then so in this case, what we're looking for is this, again, in 3D matching, we'd be looking for a configuration where basically we can have all three sets matched. So we'll start out with here, Alice, Al, and the armadillo. This means that we can't do Bob. This means that Bob can't be configured with, it can't be matched with Alice and the anymore, right? That means that this triplet is out. Bob, Alice, and the armadillo, since we've already chosen that. So we're going to go ahead and choose this triplet because it's Bob's only other triplet. Bob, Carol, and the Bobcat, which leaves this last one to be chosen that pairs Chet, Beatrice, and the canary. And so there's our three-dimensional matching. Okay. And again, obviously, we're doing this matters for things other than just figuring out happy couples and their pets, right? Also, bobcats and armadillos, very weird pets. Do not recommend. Okay. So we've got 3-sat, we've done sat, we've done three-dimensional matching. Now let's go over three. Now we have three more that we can cover in pretty quick succession. Okay? Which are vertex cover, clique, and we referred to it as Rudrata, but when it was posed, it was Hamiltonian. Okay, vertex cover. It looked like vertex lover. All right, vertex cover. So the idea here is, in vertex cover is, let's go ahead and draw this. 1, 2, 3. Go. 1, 2, 3, 4, 5, 6, 7. So here's one graph. The idea in vertex cover is to choose a set of vertices so that every vertex is covered in that set. So, here, so that every edge is connected. So here if I choose, let's see, yep. So if we now check every edge, these edges are connected to our blue dots. So I've selected these 4 nodes. Now, vertex cover is asking is basically choose some set of nodes some set of vertex such that now that every that every edge will be next to one of the chosen vertexes, right? And we can see that every edge is next to a chosen vertex now, right? Makes sense? Okay, that's vertex cover. You can reduce 3-sat into this. A very, very closely related problem that you'll be covering in the homework is clique, which is, now typically, by the way, the decision problem for the previous problem is there a vertex cover of size k or less? Clique says, can we find so what is a clique? It's a complete subgraph. So, let's go ahead and, right. So these highlighted subgraphs are each cliques of size 3. This is where we can get from any, where basically it's fully connected. It's a complete, each of those is a complete graph. Every node can get to any other node. The only edges that are missing as possibilities are self edges. If we add another edge over here, then this is now a clique of size 4, right? Or another vertice over there with the appropriate edges. That's now a clique of size 4. Make sense? Okay. And clique asks, and the clique problem asks, does it contain a clique of size k or more? Hamiltonian, we've covered that a couple times, or Rudrata, which basically says, here's a graph. Here's some graph and some edges, right? We don't know what the edges are, but there's a lot of them, right? And the answer is there a cycle that, is there a path that goes through, every edge and then lands on our beginning spot, right? Is there a cycle that visits every vertex exactly once and returns to the starting vertex? And you can reduce that, and you can get that from vertex cover. And then the last one is from set theory, which is, whoops. The last one is from set theory, partition, which says, given S is a multi-set of integers, and if I'm recalling my definitions correctly, multi-set, yep, it allows for multiple instances of an element. So think of it like a list. So think of it as it's a multi-set. In other words, it's a list of integers. Can you divide it into two subsets? S1 and S2, such that sum of S1 is equal to sum of S2. Make sense? And they are distinct. and they're distinct. S2, S minus S1 is equal to S2, right? So, and we kind of often see this as kind of a reducibility of a tree of reductions, where SAT reduces to 3SAT, 3SAT reduces to three-dimensional matching, which reduces to partition, believe it or not, which reduce vertex cover, Hamiltonian, and clique. No, I didn't capitalize them for some. I capitalized them randomly. Doesn't matter. The initial list wasn't actually 7, but these are the 7 primary ones. They were 21 problems. It's published by CARP. And I'll briefly list them before I call for a brief break. NP complete problems. Or 21 NP complete problems. CARP's 21 NP complete problems. As you can see, satisfiability, 0-1 integer programming. Then you can see clique was used to turn into a lot of other things, including vertex cover and set cover. Satisfiability with 3 literals per 3SAT, chromatic number, which is also called the graph coloring. And you can see that exact cover then went into knapsack. So there are a lot, and now there's a lot of problems. The only thing I will say is that sometimes you might read that like Tetris is NP complete or Super Mario is NP complete. Usually what they mean is NP hard. We know it's at least as hard as any NP complete problem. All right, with that, go ahead and take a break. No worries. Yeah, the lattice paths. Yeah, that was a good dynamic programming problem. So let's go ahead and take a look at this maximum path sum problem. All right, so here we've got to import this problem right now, which is unfortunate. So but let's go ahead and make this easy for us by looking at the way this is supposed to be done, which is that we have this triangle.txt. Okay, and we see that it's, again, in that triangle form. Right, so we'll go ahead and save this file as documents, GitHub, teaching, algorithms, right? And I'll call it triangle. Okay, and we see the format that it's in. So we're going to go ahead and take this. First off, okay, so first let me go ahead and save this. Euler. Documents, GitHub. Teaching, algorithms, Euler, 18, we'll call it 67. Okay, and we'll save it. Okay. Delete this file because I don't need it. And what we're going to do is that we are going to open up the triangle file. Open. And we can see that this is basically just simply everything divided by spaces, so that's awesome. We'll get rid of that last empty line just to make it easy for us. We're also going to create a new file, and what we'll do is we'll select all these, copy it, right? See, I'm just copying this right over here, and I'm going to go ahead and paste this into a file, and I'm going to call this I'm going to call this try18.txt, right, for triangle 18. That way, if it loads up on this, it will, if it's working for this file, it's going to work on the other file. Make sense? So I only have to write one program. Okay. Now, what I have to do is that I can actually def find. So I'm going to just split this up into file reading. I could just read it line by line and solve it that way, but I'm going to be boring, and I'll split it up into like a read data, given a file name, because, you know, good to remind you how to do this in Python, which is super easy. Data is equal to blank. And this also allows me to focus on the parsing and getting it into the format I want. So we've got this data. I want to return my data. And that will, and then I can, and I'll go ahead and print out read. Sorry, I'm gonna go ahead and put in all the like bits that I want to connect with the end. So data is equal to read data try18.txt, right? That's the file name. And then we'll print out the data. And that way, and if we run this right now, we'll print out an empty list because that's all we have right now. And then what we're going to do is we are going to now confirm that we are able to read the file. Text, you know, when I'm mixing names like data, and but I'm also want to read the file, which is the data, I will often refer to my file as text because that is very abstract. You know, a file is just simply a bunch of text. It's a bunch of lines that I can turn into data. Open, file name, and then super easy to do. That's all you really need to do in Python. I'll put an R for readme over here. For line in text, what we'll do to begin with this is we'll print out the line, right? Because I don't know how comfortable y'all are in Python at this point. But we read it, and there you go. Now, what's going on over here with this is that the reason that everything is like double spaced right now, why we have an empty line between everything, is because we read the line, and then what the line does is that it says, hey, there's a new line character at the end of the line. So we'll print out that new line character that you just read as well. And I'll print out a new line character on my own because that's what a print statement does by default. So, but point being is that we are reading the file appropriately. That is all we really care about, right? It's all we really care about is that we are reading this file appropriately. Okay, now that we are reading it appropriately, what we want to do is we want to, let's go ahead and do, let's keep printing this, but instead we're going to do print line.split. And by default, I think if we don't give it anything, yes, it splits it up by spaces. So 75 by itself, 95, 64, 17, 47, 80, and so on and so forth. Okay? So again, I'm going to show you I'm going to show you the very direct way to do this, and then I'm going to show you the very quick and dirty way to do this. Okay? So, or sorry, the very so line dot split is equal to, what's so funny? Did I repeat it? It's so line dot split is equal to so what I'll do is for line is I'll turn this, I'll say numbers is equal to line dot split. But again, if I print out the numbers, they're strings and I want integers, right? That's why I say it takes some time. So what we're going to do instead is, yeah. So I'll go ahead and replace line with itself, right? So print line. I'll often do that just simply because I can use it as a temporary variable, and then for x in line. Okay, so we've got, and I'll create something called numbers. is equal to a new line, and append. What we'll do here is we'll say numbers dot append int x. Let's convert it into an integer with the int function. That's how you convert it in Python. Super easy to convert it. Just toss it into the int. Then we add it to the numbers. Take this print statement, move it down here for a second before I immediately delete it. Because what I'm going to do is I'm going to print out numbers, and we can see now that all of our numbers are now integers, which is what we want. Now that we've converted each line into integers, what we can do is we can say, we can do data dot append numbers, right? Make sense? And now we can return the data, which if we print it out, we got 75, 95. So now our data is fully read, okay? Now, if I wanted to do this in an awful, dirty, but very quick way, then what I can do is I can say data dot append. So what we want to do is that we want to append some data. We want to append this line. This line gets split up into multiple fields, right? And we're left with a list of strings. But what I really want is for this list of strings to actually be integers, right? So what I'm going to do is I'm going to say map int to line.split. So this results in a list, right, of strings. This applies the integer function to all of those things. And then, does this work? Or, nah, it just gives me the map object. So I'm going to need to turn it into, and then I take each of those and I force it into a list. Because once you've got a map, the idea is that it wants you to iterate through it, and you're like, I don't want to iterate through it manually. I just want to convert it into a list. A map is kind of a data structure you iterate through. Here, I'm just saying, no, just give me the resultant. And there we go. Another way now that I think about it is we could also do data dot append, and then we can do a list comprehension over here where we say int x for x in line dot split, which might actually be a bit cleaner to do. Let's see, does that work? I mean, it's yelling at me, but I feel like it should work, so let's see. Oh, int x, right, as a function. And I need it as a function. There we go, and there you go. So yeah. And what that's saying is that we've got an inline for loop over here, for x inline dot split. Do this, and put all the results in a list together. They all work. Ideally, there's probably one that's better than the other. I bet you it's the list comprehension that's better. That's this third way. That's the best and most efficient in Python. But regardless, now we have our data, right, that we can iterate through. Okay? Okay. Now, the idea here is that we don't... Now, this problem might be, we'd probably have to... we care about what the maximum total is. We don't care about what the route is. Sorry, we don't care about what the price of the route is, okay? Sorry, we only care about the price of the route. We don't care what nodes are in it. But if we did, right, we're gonna have, then it's not too bad. All we do is that we have a, right, currently we just have basically, we're gonna have a cost, list where we've got 70, and then it's going to be 140 and 130 over here, and so on and so forth. We've got a cost, right? And we're just going to find the biggest number. But if we cared about what was in there, then we'd have a previous, just like we did for like Dijkstra's, where basically we would have, what is the previous 0, 0. And here we would say index 0 in the line above was the best way to go, and then we could recreate it that way. We can just simply list the previous index that we came from if we cared about that. We don't, but we could. Okay, so so let's go ahead and def max path, right? And again, why I put this in dynamic programming is that what we're doing is that each path is kind of a subproblem of the previous path. It's a bit more direct than some of the problems we've had to work through, but hey. Okay, so what we do is we'll make a cost, and that's equal to this. And we'll do is say for line in data. All right, so what we're going to do actually is that we're going to, so for line in data and I always forget this, index value in enumerate line, print index value, I bet you it's the other way around. All right, max path data, so we're not printing that out anymore. Okay, so, no, I got it right. Okay, so what I'm doing is I'm going to read each of these lines, so to speak. I'm going to read each line of the triangle, and then I got to go through each number in it, right? Now what I'm doing is I'm going to use my index, and I've got basically I've got the index and the value. Okay. Because I care about what index it is I need, because I'm going to need, let's see, because I'm going to need those values. In fact, I'm probably going to need it over here too. Enumerate data. Enumerate allows you to do a for each loop where you get both it gets you both the value and the index. So here, unfortunately, what I'm just going to have to do is go row column format, where this is row, and then each is a prospective column. So instead of this, it will be column for row, line, column, and then the reason being is, again, we really care about we're going to really need to refer to the previous row and the previous column. So what we're going to need to do is we're going to make a variable for each row. We're going to need to make an array called a list called row cost. Okay. And what we'll do over here is that we'll say if line, first off, I'm going to be a bit lazy over here, but also just reinforce a programming concept you may have forgotten. If row equals 0, cost is equal row cost dot append line 0, continue. Okay, basically if I'm reading the very first line, I want to initialize it properly, because otherwise because all the other algorithms are going to require me to look above, right? Make sense? Okay. So, let's see. Okay. So, let's see. So what I need to do is figure out for each line, where is it coming from? Okay, so I've got this triangle over here. Now, it's going to get the current value plus the value previous above, the value, so this is index 0. It's going to get index 0. This location is also going to get index 0. Sorry, this is column 1. And it's going to get row. So first off, this got the same column 0, and row minus 1. This also gets row minus 1. In other words, the row above me. But it also gets column minus 1, right? This value gets row above me. This gets the same row and row minus 1, and this gets row minus 1. This value gets, sorry, I'm not saying row, but it's column. So this gets the row, so they all go referred to, in order to get the path, they go to the row above them. This one, it only has one path. It's coming from this square. This has two paths, right? Right? It's coming from 95 or 74 or 64. So to do that, it's got to look at column minus 1 and the same column. Similarly, this one has one path at column minus 1, right? So this is becoming a kind of geometric problem or an indexing problem over here, more than anything else. Making sure we got the appropriate index. Okay, I think though any pattern we need is going to be able to be figured out by this. So this one, again, same column. 35 is going to get the two above it. 87 is going to get the 2 above it. So everything but the first one and the last one get the 2 above it. So where can I find the 2 above it, so to speak? Okay. Well, 18 gets that. 35 gets 17 and 47. 87 gets 47 and 82. In other words, it always looks at the same column and the column minus 1. So, in other words, you've got two values that it cares about. So for every column, it's going to look at cost A. It's got two choices, and we're going to ignore the endpoints for right now, and we'll see if we can't figure out a way around them. Okay, cost A is going to be cost, I'll just call it A, right? Is cost of row, we look at the row above us, and row above us and the column behind us. And B is equal to the cost above us and the same column as us, right? Okay, and then what we'll do is we say row cost dot append the max of either the row cost for our square to get to us is equal to the row cost of whatever's bigger, A or B, right? That's what max does. Tells me which one's bigger. Make sense? Plus the value of this square. So the cost to get into the cost of our square of this path so far is the cost of where I am plus the cost of whether it's better to go to this point or this point. Make sense? Following so far? Okay. So now, question is, how do I deal with out of bounds issues? Well, let's see. I think I'm going to be a bit clever about it, and what I'll do is for A, going one back, right? So if I'm at if my column is at column 0, right, then this will be fine. If I'm at column 0, this is going to be fine. But -1 would give me -1, which would wrap around, and that would be, in Python that wraps around. -1 gets you the end, right? So instead what I want to do is I'll be a bit cheeky and say the max of this value in 0. Makes sense? So if this goes out of bounds, if it goes less, if this would result in a negative value, instead go to 0. Make sense? Okay. Is that good? Probably not. I don't. Okay. What?
That's kind of dirty.
I am great at dirty. Okay. Similarly for B, right? Because this is jagged, the last index is always not going to have this. So if so here we're going to want to do min of column and len of the line, however long this line we're looking at -1 is. Again, super dirty. What is this doing? This is saying, hey, if your column, if the column is out of bounds, I don't want the out of bounds. I just want the very last thing, which will be, by the way, the same as this over here. Length of line. Hold on a second. Length of line -1. So that would be, so if this is 5, I want index 4, which wouldn't work. So -2. There we go. All right. Let's see if it. Let's go ahead and see if it works somewhat. Print cost. All right. I haven't done anything yet. Now once we're done with the row cost dot append row cost. Index out of bounds error, of course. Okay. So index row -1, index out of range. It's saying cost. Hold on. If row. Okay. Let's see. We'll print row. We'll print out the row. So we're in row 1. Hold on. Oh, okay. There we go. Boo. Okay. Print row, and we'll print out what we have so far. Okay. Because of course it doesn't get added to the here. Yes. Okay, I see what happened there. I had a
Oh, it is so convenient.
Didn't have any values there. Okay. And then print max of cost -1, 1074. 1074. All right, what in the world did I just do? Okay, so first off, this said find the biggest value in the bottom row and print it, right? Find the biggest value. Gives me the bottom row of costs, right? It gives me this, and I just simply say find the biggest thing and print it out. Okay, so what goes on over here? So let's walk through this algorithm again. Cost. So for every row, for every line that I read in, I create a line to hold its costs and store those costs to reference later. If this is the very first row I'm looking at, then I don't want to get into anything over here that's going to be annoying. You know, I don't want to have to risk out of bounds issues, although I do wonder. Yep. I don't want to have to deal with any out of bounds issues, so what I do over here is I just simply append it, right? And then for anything other row that I know that I can look at the row above me, what I do is I look at the row above me, and again, what this did is that it said, hey, if your column is currently at index 0, then I want it to stay at index 0. If your column is referring 0 is going to be 0, I don't want to get -1, so keep it at 0. Similarly, if this value would be out of bounds, I want to get the last value of the previous line, hence the -2, because again, this is length 5. This current row is length 5, meaning this is index 4, and the only value I'd want to look at is index 3. So -2 of the size. And then I just simply say, hey, those two values you read, you know, which one is bigger? I mean, again, if we want it less dirty, we can do a couple if-else statements where basically we say, hey, if A is equal to 0, if col is, if col -1 is greater than or equal to 0, then we can say A is, is this cost, right? But I like the way I did it because it made sense to the way I was thinking right now. Again, which is terrible. But now we can try it out on the actual triangle.txt. And if we run it, it runs and gets us 7273, which, according to problem 67, is the correct answer. Now, the reason why we're able to do this, again, it's not possible to try every route to solve the problem, as there's 2 to the 99 possible routes. There's 100 rows, and each row adds twice as many paths.
Essentially using the idea of like dynamic programming.
Yeah, what I'm doing is that I'm starting at the beginning. I'm using efficient subproblems. I'm starting at the beginning and going forward and using the data from each previous subproblem of, okay, and you can think of the subproblem as, okay, what is the most expensive value to get to this point? What is the most expensive value in this line? What is the most expensive value in this line? Or the most expensive value to get to this square. Each square gets computed once. So if we have n number, so that you can think of this as either linear time or as quadratic time, depending on and again, it always depends on what n is for your input. If n is the number of items, this takes O of n time. If n is the number of lines, this takes n squared lines, as each line can have up to n lines in it. Right? So either way, it is what we refer to as, this is now an efficient algorithm because it runs in polynomial time. Let me stop recording and I'll dump it on Discord.